Hello everyone, I welcome you all to my YouTube channel Organic Chemistry by Aleena. In the previous videos, we have already completed the first case of delocalization, that is pi sigma pi type. In this video, we will start with pi sigma lone pair type delocalization and we will solve different questions related to this conjugation. And we might take up pi sigma positive or negative charge if time allows. Okay, so let us see. The first question is this. Okay, it is an amine, a primary amine. As you all can see, it is a primary amine. And what type of primary amine is it? It is a vinyl amine. I hope you all are aware of this term vinyl. Vinyl means when the functional group or substituent is attached to sp2 hybridized carbon of a carbon-carbon double bond. Okay, so this is a vinylamine, and similarly this is a methoxy ether and it is a vinyl ether. Okay, so here if it is very clear that we have a pi sigma lone pair type system, so delocalization is possible. So how will we draw the resonance contributors of this structure? The first structure, we will delocalize this lone pair over this bond and see how the pi electrons of this pi bond shift. Okay, so this lone pair comes here. When this comes here, the pi electrons shift to this carbon. Okay, we draw the resonance symbol, a double-headed arrow, and draw the first contributor as this, NH2. Now, since the lone pair of nitrogen has involved itself in delocalization, nitrogen acquires a positive charge. Alright, I hope this is clear. So, when this negative charge comes back to its initial position, the nitrogen atom pulls back the pi electron density in the form of lone pair and we get the structure back. That is this. So, the hybrid will be, the basic structure remains as it is. Okay, and a pi bond character here as well as here. Okay, so on both these carbons, okay, on both these bonds, this bond and this bond, there is a pi character here. Okay, because of delocalization of this lone pair and this pi bond. Now let us talk about charge separation. This carbon here in this contributor has a negative charge, so in the hybrid it will have a partial negative charge. Nitrogen, because it has delocalized its lone pair over this bond, hence it acquires a positive charge in this contributor and we'll have a partial positive charge in the hybrid as well. Okay, so this is the hybrid of this compound, this vinylamine. Similarly, as you have delocalized the lone pair of nitrogen over this bond, you can delocalize one of the lone pairs of oxygen to this bond, right? Oxygen always prefers to form two covalent bonds and two non-bonding electron pairs remain as lone pair on the oxygen atom. So, one of the lone pair involves itself in the delocalization process, the other remains as a localized electron pair. Okay, this is a localized electron pair and this delocalizes here. Okay, when this comes here, these pi bonds shift here, these pi electrons shift here. Okay, so you can draw the resonance contributor of this structure in the similar way as you have drawn for this vinylamine. Okay, so this is a homework question for you. Now moving on to this. What is this? This is an amide. This is the next question that we have, and here we can see that the structure has an amide linkage. Amide linkage is when an amine moiety is directly linked with a carbonyl group. Okay, when nitrogen of the amine group is linked to carbonyl carbon of the carbonyl, this moiety. So this is the amide linkage. This is found in most of the proteins as the peptide bond. Okay, this is the very famous peptide bond that you find in amino acids. Okay, amino acids and proteins. Amide bond is the peptide bond. So nitrogen here has a lone pair which is separated through a sigma bond from this pi bond. Okay, so we have a lone pair sigma and pi, or pi sigma lone pair type system. So this nitrogen again gives its electron for delocalization. The lone pair comes here, the pi electron density shifts to the oxygen atom, and we have the contributor as this. Okay, positive and a pi character here, because this lone pair has come here, and as the result of which this pi electron density has shifted. Okay, so this is a contributor of this amide. This PR group, if you are wondering what is this is nothing but propyl group. Okay, so this nitrogen atom here has 1, 2, first, second and third, a 3 carbon straight alkyl chain attached to this center. Okay, this is the structure. Okay, PR is the abbreviation for propyl group, and here we have not mentioned anything, no substituent is written here. That means we have a methyl group at this position. Alright, so this is the contributor. You can draw the contributors as this as well. First, this carbonyl group pulls the oxygen of carbonyl group pulls the electron density towards itself, creating a carbocation. Okay, this is the first contributor, and to stabilize this positive charge, the lone pair of nitrogen gives its electron at this bond. Okay, so NH and PR. So you can say this amide, this compound has 3 contributors: first contributor, second contributor and third contributor. So there are 3 resonance contributors of this structure, and to draw the hybrid, you can make the hybrid like this, the basic structure remaining as it is, and the pi electron density spreading over this bond and this bond, and a partial positive here, a partial negative here. Okay, I hope you are getting how we have drawn hybrids so far. Now there are these 3 aromatic compounds here that we have. This is phenol, this is aniline, and this is anisole. Okay, this is anisole, and its IUPAC name is methoxybenzene. This is aminobenzene, and this is hydroxybenzene. Okay, phenol, aniline and anisole. Okay, these 3 are aromatic compounds. Now all these 3 groups, this group and this group, they have the electronegative atom attached to the benzene ring. Okay, so these will have a minus I effect but a plus M effect, because all these groups have a lone pair attached. Okay, these type of groups have a plus M effect and a minus I effect. Now let us talk about resonance in phenol and the resonance contributors of aniline and anisole. You can draw very well taking reference from the contributors of phenol. Okay, now this is the structure of phenol. This lone pair comes here and this pi bond shifts here, giving us our first contributor, double bond OH, a negative charge, and oxygen, since it has given one lone pair in delocalization, it gets a positive charge. The other lone pair remains as a localized lone pair. This bond remains here, this bond remains here. Okay, the next contributor comes by delocalizing, by moving forward this negative charge. Okay, this negative comes here and this pi bond shifts here. to maintain the valency of carbon of 4. Positive. Now this negative moves here and these 5 electrons shift here. Negative, double bond, OH, positive. Now the last contributor will be when this negative charge comes here and oxygen pulls back its electrons in the form of lone pair back. So here we have a pi bond here, and OH. Phenol back in picture. Okay. Now drawing the hybrid of phenol as this. The pi electron density is across this benzene ring, through this bond, and a partial positive here and partial negative where negative charge on ortho, para, and again ortho. So electron richness at ortho and para positions. Okay, so you have seen how hydroxy groups how hydroxy group acts as a plus M group, giving its electrons to benzene ring. Okay, this lone pair has shifted away from oxygen atom towards the ring, and hence we call this hydroxyl group as a group showing plus M effect or plus mesomeric effect. Alright, now the contributors of aniline and anisole you can draw very well. You take the reference from the contributors that I have drawn for phenol. In the similar way, you can draw the contributors for the resonating structures for aniline and anisole. Okay, the hybrids will be drawn in the similar way. Now this is another structure that we have now. This is a 5-membered heterocycle. Its name is pyrrole. Okay. Now this here we have a lone pair. This is the sigma bond and this is the pi bond. Or if you see from here, lone pair, sigma bond and pi bond. This structure is symmetrical, right? Through this this bond and nitrogen. So you can start drawing arrows from either side. Let us see how we draw the contributors of this structure, pyrrole. When this lone pair comes here, this pi bond shifts here, giving us our first contributor as this. Negative charge on this carbon, double bond here, and a positive on nitrogen because it has given up its lone pair in delocalization process. Negative moves forward. Okay, this pi bond comes here and we get another contributor. Positive, double bond, negative. Okay, now when this negative moves here, nitrogen cannot have a pentavalence because it will be an invalid Lewis structure. So this pi bond has to shift here. Okay. Double bond, negative, and a positive on nitrogen again. Now this negative moves here and these pi electrons shift here. Positive, double bond, negative, double bond. Now you can draw the another contributor as this. When this negative moves here, nitrogen pulls back its pi electron density in the form of lone pair. Okay, lone pair comes back, pi bond here, so we get pyrrole back. Okay, the hybrid, remember that even if the question does not ask you to draw hybrids, it is a good practice to always draw them. Okay, now pi electron density over all 4 carbons and nitrogen. Okay, and what about charge separation? Nitrogen, in all the contributors, nitrogen bears a partial positive charge, so partial positive on nitrogen. And what about carbons? This carbon has partial negative, so partial negative. This carbon has partial negative, so partial negative here. This carbon has partial negative, so partial negative over this carbon and partial negative over this carbon as well. So all carbons are All carbons bear a partial negative charge and nitrogen has a partial positive charge in the hybrid of pyrrole. Okay, so this is the hybrid. These two structures are also examples of pi sigma lone pair type delocalization. In the previous lecture, I briefly told you about linear conjugation and cross conjugation. So you just tell me, looking at these two questions, which one will be the example of linear conjugation and which will be the example of cross conjugation. In cross conjugation, there are three groups A, B, C. A is in resonance with C, B is in resonance with C, but A and B are not in resonance with each other. Okay. And in linear conjugation, all three groups are in conjugation with A is in conjugation with B, B is in conjugation with C. Okay, in linear conjugation. So if you see here, we have lone pair, sigma bond, pi bond, sigma bond, pi bond. Okay, so here over this system, we have a pi sigma lone pair type delocalization, and on this part of the molecule, we have pi sigma pi type delocalization. So let us see how we draw the contributors of this structure first. Let us call this as A structure. Okay, NH2. When this lone pair comes here, this pi density shifts to this carbon. Okay, and we get the first contributor as this. This pi bond remains here, negative charge on this carbon and a pi bond here, and nitrogen gains a positive charge. Now this negative shifts here and this pi bond shifts to this carbon, and we get the third contributor as this. Negative here, double bond here. Okay, when this negative comes here, this pi bond will shift here, and when the negative charge over this carbon shifts here, nitrogen gets back its electrons. Okay, the reverse of this happens. Now you see this is an example of linear conjugation because all three groups are conjugated with each other in a linear manner. A gives here, then B, then C. Okay, there is linear delocalization. All three groups are involved in delocalization at the same time. Okay, this is the hybrid of this structure. NH2, pi electron density here, 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 and here. Okay, all 1, 2, 3, 4, 5. All 5 bonds have pi electron density, pi character in them, and the charge separation is as follows: partial positive on nitrogen and partial negative here, partial negative here on this carbon. Okay, so this is the hybrid. This is the hybrid of this structure. Now let us see here. Let us call it group C. Okay, this is group A, this is group B. You'll understand cross conjugation through this example. But first, it is important to note that I hope you have already noticed this, that these two compounds are isomers of each other. Okay, the condensed formula of these two compounds is exactly same, only this is a secondary amine, this is a primary amine. Okay, here if you see, if I this is a lone pair sigma pi sigma lone pair type system here over this moiety, and lone pair sigma pi sigma lone pair over this part also. Okay, so we have two pi sigma lone pair type delocalizations possible. Let us see how we draw the contributing structures. Okay, when C and B are in resonance with each other, A behaves as a localized bond, and we have this lone pair coming here and this pi electron density coming over this carbon. Okay, so negative charge here. Alright, this is the first contributor, and if you see, if A and C are in resonance with each other, we can draw the contributor as, when this lone pair comes here, this pi electron density will shift here. So negative, double bond NH, and single bond, double bond, double bond. Okay, when A and C are in resonance with each other, B is behaving as a localized bond. However, none of these bonds is a localized one. All three are in resonance with each other, but not simultaneously, because this is an example of cross conjugation. See, when when C and B were in resonance with each other, na, A was not in resonance with C, right? So this proves the definition of this. ABC groups present, A and C in resonance with each other, B and C is in resonance with each other, but A and B, these two bonds are not in resonance with each other. Okay, and none of the hybrid is such that the charge separation demands contribution from A, है ना? इधर तो क्या था? अगर आप इधर देखो A, B, C, अगर इधर बोलो A और B आपस में रेजोनेंस में है, B और C आपस में रेजोनेंस में है, लेकिन A और C तो इधर है नहीं. लेकिन एक कंट्रीब्यूटर की वजह से यहाँ पर जब कंट्रीब्यूशन हुआ, जब नाइट्रोजन ने अपना लोन पेयर इधर दिया और यहाँ पर नेगेटिव चार्ज आया, तो इस नेगेटिव चार्ज ने फर्दर आगे मूवमेंट की, क्योंकि डिलोकलाइजेशन आगे भी पॉसिबल थी. ठीक है, तो एक रेजोनेंस फॉर्म की वजह से दूसरी रेजोनेंस फॉर्म एक्शन में आई और डिलोकलाइजेशन पॉसिबल थी. बट इधर अगर आप C और B को डिलोकलाइज कर रहे हो तो यहाँ पर ही रह जा रहा है स्ट्रक्चर, इसका कोई इन्वॉल्वमेंट नहीं आ पा रहा चार्ज सेपरेशन से, राइट? तो इधर क्रॉस कॉन्जुगेशन है. ऑलवेज रिमेंबर दैट लीनियर कॉन्जुगेटेड जो स्ट्रक्चर्स होते हैं, दे आर मोर स्टेबल देन क्रॉस कॉन्जुगेटेड स्ट्रक्चर्स. ओके, दिस इज द डिफरेंस इन स्टेबिलिटी. The structures which have linear conjugation, they are more stable than structures which have cross conjugation. All right, this is important for jam point of view. All right, but it is a part of GOC, so JEE people and NEET people can also see this. Now, there are some consequences of delocalization over hybridization of the heteroatom, which involves its lone pair and delocalization. All right, let us see. Let us study about this. First, we have a question. Out of structure A and B, which one is more stable? ठीक है, A structure ये है जो एक विनाइल अमीन आप देखकर ही बता सकते हो. However, the B structure is an allyl amine. I already told you about the vinyl term. Let us see what allyl means. Okay, allyl means there is a double bond. Okay, to the sp2 hybridized carbon of the double bond, we have an sp3 hybridized carbon. And to this sp3 hybridized carbon, we have the substituent attached. Alright, sp2, sp2, then sp3, and then to this sp3 center, we have the substituent or the functional group attached. So this is an allyl. This is an allyl structure, okay, an allyl amine. And vinyl, on the other hand, they have the substituent directly attached to sp2 carbon of the carbon-carbon double bond. Okay, so this is vinylamine, this is allylamine. Out of these two structures, which one do you think is more stable? You can see you have come so far in the delocalization concept and the resonance concept. This structure has a pi sigma lone pair type delocalization possible. However, in this structure, if you see, the pi bond and the lone pair, they are separated by 2 sigma bonds. Right, there is a distance of 2 sigma bonds between this pi bond and this lone pair, so no delocalization possible. No delocalization possible. So this lone pair is confined to this nitrogen, and this pi bond is confined to this carbon and this carbon. So this is a localized structure, of course, localized structure. However, this is a delocalized one. And I already told you, and you are very well aware of the fact that delocalized structures are more stable than their localized counterparts. Okay, so this delocalized amine is far more stable than this localized amine. Now let us talk about hybridization. ओके, पहले आपको ये पता होना चाहिए कि इधर और इधर, in this structure and in this structure, this is a simple N-ethylamine. N-ethylamine. Okay, this is a saturated amine, this is an unsaturated amine. There is a double bond here, there is no double bond here. Okay, so now here we have both these amines are primary amines in the first place. Okay, this nitrogen has what type of hybridization? An sp3 hybridization, because 3 sigma bonds are there, one about N and C, one this CN bond, and 2 bonds across N and H, 2 bonds of NH type. Alright, and 1 lone pair, so 3 plus 1 accounts for sp3 hybridization, which means a tetrahedral structure. A tetrahedral structure, or TD, let us write. Here we have, here no delocalization is possible, इधर delocalization possible है, but इधर देखते हैं, हम पहले देखने में क्या लग रहा है कि इधर hybridization क्या होगी. हम steric number calculate करते हैं. Steric number gives us the estimate of number of hybrid orbitals, or we call the steric number as the Vesper count. Okay, this steric number is number of hybrid orbitals or the Vesper count. अब इधर देखते हैं, 3 सिग्मा बॉन्ड्स है, एक सिग्मा बॉन्ड इधर और 2 सिग्मा बॉन्ड जो NH बॉन्ड्स के बीच में है, तो 3 सिग्मा बॉन्ड्स प्लस नाइट्रोजन हैज 1 लोन पेयर, तो 3 + 1 sp3 हाइब्रिडाइज्ड. ठीक है, अभी ये स्ट्रक्चर हमें देखने पर ऐसा लग रहा है कि नाइट्रोजन sp3 हाइब्रिडाइज्ड होगा, बट क्योंकि नाइट्रोजन का लोन पेयर डीलोकलाइजेशन में इन्वॉल्व है, तो ये हाइब्रिडाइजेशन नाइट्रोजन की sp3 कंप्लीटली नहीं रहती, नॉट प्योरली sp3. नाइट्रोजन का लोन पेयर, नाइट्रोजन की हाइब्रिडाइजेशन इस स्ट्रक्चर में जहां डीलोकलाइजेशन पॉसिबल है, प्योरली sp3 नहीं रहती. क्यों नहीं रहती? बिकॉज आई ऑलरेडी टोल्ड यू कि डीलोकलाइजेशन का देयर इज अ प्री रेक्विजिट फॉर डीलोकलाइजेशन टू टेक प्लेस. व्हाट इज दैट प्री रेक्विजिट? वो प्री रेक्विजिट क्या है कि यू हैव टू हैव पैरेलल p orbitals adjacent to each other. Okay, adjacent to each other. Okay, let me write the short form of each other as E/O. So parallel p orbitals adjacent to each other. अगर parallel p orbitals नहीं होंगे तो हाइब्रिडाइजेशन तो डीलोकलाइजेशन नहीं होगी. ठीक है, क्योंकि जब पैरेलल p orbitals होते हैं तभी तो साइमल्टेनियसली इधर भी ओवरलैप हो जाता है और इधर भी ओवरलैप हो जाता है, थोड़ा पाई कैरेक्टर इधर भी डेवलप हो जाता है. वो एग्जाम्पल याद है ना, यू रिमेम्बर दैट एग्जाम्पल वेर आई टुक दिस क्वेश्चन, डबल बॉन्ड CH, सिंगल बॉन्ड CH, डबल बॉन्ड CH, सिंगल बॉन्ड CH3. दिस वाज द एग्जाम्पल ना व्हेन वी स्टार्टेड द डीलोकलाइजेशन कॉन्सेप्ट. इधर भी p कैरेक्टर, इधर भी p अनहाइब्रिडाइज्ड p ऑर्बिटल, अनहाइब्रिडाइज्ड p और अनपेयर्ड स्पिन ऑपोजिट डायरेक्शन में होते हैं, तो इधर तो पाई बॉन्ड है ही, लेकिन इधर भी स्कोप होता है पाई कैरेक्टर का, तभी तो हम बोलते हैं डीलोकलाइजेशन हो गई. इफ यू डोंट रिमेम्बर, जस्ट गो टू दैट प्रीवियस वीडियो, मे बी वीडियो नंबर 5 or 6, एंड जस्ट have a brush up of this concept. So prerequisite is that you have to have parallel p orbitals adjacent to each other, or on adjacent atoms you have to have parallel p orbitals. तो अगर नाइट्रोजन के पास हमारा p ऑर्बिटल होगा पैरेलल इधर, अगर लोन पेयर अनहाइब्रिडाइज्ड p ऑर्बिटल में होगा, तो यहाँ तो ऑलरेडी एक अनहाइब्रिडाइज्ड p ऑर्बिटल है ड्यू टू sp2 हाइब्रिडाइजेशन, तभी तो हमारे यहाँ पर डीलोकलाइजेशन हो पाएगी, है ना. यहाँ पर नाइट्रोजन का लोन पेयर अगर अनहाइब्रिडाइज्ड p ऑर्बिटल में होगा, तभी तो देयर इज अ स्कोप ऑफ डीलोकलाइजेशन प्रोसेस. अगर यहाँ पर हमारा नाइट्रोजन का लोन पेयर ही p ऑर्बिटल में नहीं है और सपोज वो sp3 हाइब्रिड ऑर्बिटल में चला जाता है, तो sp3 हाइब्रिड ऑर्बिटल तो 109 डिग्रीज की बॉन्ड एंगल बनाते हैं, 109 डिग्रीज की, तो वहां पर तो एक टेट्राहेड्रल टाइप स्ट्रक्चर बन रहा होगा. तो इन p ऑर्बिटल्स के पैरेलल तो वो हाइब्रिड ऑर्बिटल नहीं आ सकता किसी भी तरीके से. ठीक है। तो जहां पर भी डीलोकलाइजेशन का प्रोसेस होता है वहां अगर हाइब्रिडाइजेशन sp3 पॉसिबल भी होती है इधर किसी फंक्शनैलिटी की, तो स्टिल उसका लोन पेयर प्रेफर करता है, लोन पेयर प्रेफर्स टू गो इनटू अनहाइब्रिडाइज्ड p ऑर्बिटल, ठीक है। ताकि अनहाइब्रिडाइज्ड p ऑर्बिटल जाहिर सी बात है वो इसके पैरेलल होगा, और जब वो पैरेलल होगा तभी डीलोकलाइजेशन होगी, और डीलोकलाइजेशन लोअर्स द एनर्जी ऑफ द कंपाउंड, ठीक है। जब कंपाउंड की एनर्जी कम हो जाएगी तो जाहिर सी बात है इट विल बिकम स्टेबल, ओके। क्योंकि डीलोकलाइजेशन की वजह से स्टेबिलिटी काफी ज्यादा आ रही है, तो वो हाइब्रिडाइजेशन को sp2 और sp2 को प्रेफर करता है देन sp3 टू गेट gain of an unhybridized parallel p orbital, okay। So always remember जहां पर भी delocalization का scope होता है, wherever there is a scope of delocalization, तो जो lone pair होता है involved in delocalization, it prefers to go into unhybridized p orbital. This is very very important, okay। So if someone asks you कि इस नाइट्रोजन की actual hybridization क्या है, so you will say it is approximately sp2, okay। It is not completely sp2, it is neither completely sp3, it is between these two, more on the sp2 side, okay। क्योंकि एनर्जेटिक्स इसी को फेवर करते हैं कि जब नाइट्रोजन का लोन पेयर अनहाइब्रिडाइज्ड p ऑर्बिटल में जाएगा तो डीलोकलाइजेशन पॉसिबल होगी, एंड व्हेन डीलोकलाइजेशन इज पॉसिबल द ओवरऑल एनर्जी ऑफ द कंपाउंड गेट्स लोअर एंड द स्टेबिलिटी इंक्रीजेस, ओके। सो लेट अस सी। अब ऐसे क्वेश्चंस काफी बार आ जाते हैं कि आपको बताना है इन सब स्ट्रक्चर्स में जहां पर भी पाई सिग्मा लोन पेयर टाइप डीलोकलाइजेशन पॉसिबल है ना, वहां पर जो लोन पेयर है जिस भी हेटेरो एटम का है दैट विल बी sp2 हाइब्रिडाइज्ड, ओके। और लोन पेयर विल बी इन अनहाइब्रिडाइज्ड p ऑर्बिटल, ठीक है। अब इधर आपको बताना है फिनॉल में हाउ मेनी sp2 सेंटर्स, number of sp2 hybridized atoms you have to tell in phenol. Total atoms, they are not asking you about carbons. So all these carbons in the benzene ring over the phenyl group are sp2 hybridized. So 6 carbons are there, so 6 atoms तो हो गए। अब कुछ बच्चे इस ऑक्सीजन को, इस स्ट्रक्चर को अज्यूम करके sp3 कंसिडर कर लेंगे, 1 लोन पेयर, सेकंड लोन पेयर, 1 सिग्मा बॉन्ड, 2 सेकंड सिग्मा बॉन्ड, सो स्टेरिक नंबर 4, और उसको sp3 का अज्यूम कर लेंगे, बट ऐसा नहीं है। आई टोल्ड यू क्योंकि ये फिनॉल में ऑक्सीजन एटम हैज अ स्कोप ऑफ डीलोकलाइजिंग इट्स लोन पेयर ओवर दिस फिनाइल रिंग, सो आप इसके फर्स्ट कंट्रीब्यूटर को अज्यूम करना, इधर पाई कैरेक्टर अज्यूम करना, और नाइट्रोजन का एक, ऑक्सीजन का एक ही लोन पेयर कंसिडर करोगे फर्स्ट। सो स्टेरिक नंबर इस स्ट्रक्चर के हिसाब से या फिर किसी भी इन सब स्ट्रक्चर के हिसाब से आप कैलकुलेट करोगे, बट इस सिग्मा बॉन्ड को और 2 लोन पेयर्स को एक साथ काउंट मत करना, ठीक है। इसको sp2 हाइब्रिडाइज्ड you will consider this oxygen atom, this nitrogen atom will also be considered sp2, this oxygen atom will also be considered sp2 because the lone pair of all these heteroatoms are involved in delocalization, ठीक है। तो number of sp2 hybridized atoms क्या होंगे, 6 of this benzene ring, 6 carbons of this benzene ring and 1 of this heteroatom, so number of sp2 hybridized atoms are 7. इधर how many sp2 hybridized, this oxygen is sp2 hybridized, this carbon is sp2 hybridized, and this nitrogen's lone pair which is involved in resonance, this is also sp2 hybridized. So 3 sp2 hybridized centers, okay. Here also 1 sp2, second sp2, third sp2, so 3 sp2 hybridized. Again here also इसको भी आप जब solve करोगे, because this is a homework question, these two are also homework questions, but number of sp2 hybridized atoms में आप ऑलवेज उस एटम को भी काउंट करोगे जिसका लोन पेयर डीलोकलाइज हो रहा है, ओके। नाउ यस, अब देयर इज वन थिंग दैट आई हैव नॉट टोल्ड यू अप टिल नाउ, दैट इज पहले मैंने आपको बोला था कि एक इलेक्ट्रोनेगेटिव एलिमेंट जो है, when there is a choice given of delocalizing electrons towards the electronegative atom or away from the electronegative atom, you always move the extra charge towards more electronegative atom, है ना? This was a rule ना? There was a rule that if you are given a choice in delocalizing electrons, always you move the extra charge towards the electronegative element. But अभी हम क्या कर रहे हैं? इलेक्ट्रोनेगेटिव एलिमेंट से चार्ज डेंसिटी को, मतलब उसके लोन पेयर को, उससे दूर लेके जा रहे हैं पाई सिग्मा लोन पेयर टाइप में. ये रूल हमने पढ़ा था पाई सिग्मा पाई टाइप डीलोकलाइजेशन में. ऑलवेज रिमेंबर दैट जब आप डीलोकलाइज करते हो, whenever you delocalize the extra charge, be it a pi bond, a lone pair, a negative charge, तो ऑर्डर क्या होता है? You have to delocalize the extra charge. ठीक है, अब वो एक्स्ट्रा चार्ज क्या हो सकता है? या तो एक पाई बॉन्ड हो सकती है. एक्स्ट्रा चार्ज के बारे में हम बात कर रहे हैं, तो पाई इलेक्ट्रॉन्स हो सकते हैं, either they can be a negative charge or you can have a lone pair. ठीक है, तो ऑर्डर क्या होता है? आप सबसे पहले, अगर एक कंपाउंड में तीनों ही चीज अवेलेबल है, तो सबसे पहले जो सबसे लूजली बॉन्डेड इलेक्ट्रॉन्स होंगे, दे विल बी डीलोकलाइज. ठीक है, सबसे ज्यादा एक्स्ट्रा चार्ज क्या है? नेगेटिव की फॉर्म पे. सो फर्स्ट यू विल डीलोकलाइज द नेगेटिव चार्ज, then you will delocalize the lone pair, third you will delocalize the pi electrons. Okay, so this will be the order. ठीक है, negative charge, you delocalize the negative charge, then you delocalize the lone pair, then you delocalize the pi bond. Okay, this is the order. So this was about today's class. So thank you for watching this video. I hope you are getting all the steps that are involved, and I hope you will get fluent in drawing the resonance contributors through the end of this series. Thank you so much. Please subscribe to my YouTube channel, like this video and share it to your friends and other acquaintances studying chemistry. Goodbye for now, and yes, let's meet in the next video.